Hello guys, welcome to Physics Crack. This is day 1 of my new series called Daily Quantum Mechanics, and in this video we are going to study about linear vector spaces. So let's get started. So in this video we are going to know what do we mean by a vector and what do we mean by a linear vector space. So if you have taken any elementary physics course before this, then when I say the word vector, the image that comes to your mind immediately is that of an arrow which is having a particular length and it is pointing in some direction. Now that is a good example of a vector. I'm not saying that it is wrong, but it's more a limited definition of a vector because an abstract vector in the pure mathematical sense is much more than just an arrow, and that is what we are going to see in this video. So first of all, I would like to say that vectors that represent physical quantities which you are familiar with, like displacement, velocity, force, torque, or the electric field and so on, these can be represented in 3D using an arrow which is pointing in a defined direction and having a specified length. Now this is something that most of you will already know, and it's not wrong obviously, but it's a bit limited definition of a vector, and so therefore we should note that not all mathematical entities that we consider as vectors can be represented as arrows. Okay, so we cannot represent a vector as an arrow in all the cases. There are some instances or examples of mathematical objects which satisfy the definition of a vector, but they are not arrows, or it cannot be represented as arrows because it will not make any sense in that way. And we are going to see some examples of these as well as we move on into the future videos. But in this video we are going to strictly stick with just the definition of what we mean by a vector space and what we mean by vectors. So that is the agenda for this video. So let us straight away go to the definition. So the definition, a strictly mathematical definition of a vector space, in fact a linear vector space, which I'm going to denote it using this symbol, which is a capital V with a line. So a linear vector space V is a collection. So when we say collection, it means it's basically a set of some objects. Okay, so it's a collection of some objects which I'm going to denote in this manner, and this notation will be clear when we discuss about it in detail soon. So these objects which I am denoting like this, so the way I denote it is I put a symbol which is a line, vertical line, and a greater than symbol, and the name of that object is written inside these two symbols. So for example, this is the object whose name is 1, this is an object whose name is 2, this is an object whose name is V, and so on. These objects are called vectors. Okay, so now we have what we mean by a vector. Vectors are nothing but elements of a set which we call as a linear vector space. So when I say that these are elements of a set, these elements can be arrows, which we all know already, but it can be some other things as well, like a 2 cross 2 matrix or an n cross n matrix and so on, which cannot be represented as arrows, or it can be functions, real or complex, and these examples we are going to see in the future videos in more detail, but now we are just going to stick to the definition of what we mean by a linear vector space. So the vectors are nothing but elements of a set. Okay, so if you take an example for if you say a set of vowels, then these are just, so you already know, so it doesn't make any sense to assign any properties to these elements as such, but we can define some operations on these elements, and that is what is given in these 2 points. So for example, if you consider in our case vectors, which are elements of a set called vector space, then you cannot uh, associate these vectors or these objects and say that these vectors are real numbers or these vectors are complex numbers and so on, because it simply doesn't make sense. It is like saying that a is a real number, or a set in, if you take a set of chocolates and you're saying that this chocolate is real and this chocolate is complex and so on. So that doesn't make sense. But what makes sense is to assign those properties such as real and complex to the to numbers which multiply with these objects, okay, such as this a which I have shown here. So first let us see the definition of vector space, where so it's basically a collection of objects which are called vectors, for which there exists, okay, it means that we can define a set of operations wherein we can define vector sum. Now depending on what these objects are, the way we add them is also going to the rules for this addition is also going to change. So we have to be careful there. So I have not yet defined how exactly we add them, but all I'm saying is that there must exist a rule for adding vectors, and there must exist a rule for multiplying a vector with a scalar, okay, and a scalar is nothing but a number. So a vector space should have these two uh, operations which can be defined, and plus it should also have these features, okay. So what are these features? The uh, the vector space must be defined in such a way that all the vectors must be closed under addition and scalar multiplication. What it means is that if V is an element of the set capital of the vector space V, and the vector W is an element of a vector space V, then the vector sum of V and W must also be element of vector space V, and similarly, if this vector V is an element of vector space V, then if I multiply it with a scalar or a number which I call A, then the result of that multiplication must also belong to the set V, okay. So that was the property of vectors being closed under addition and scalar multiplication. So another property is that they must be distributive, which means that if we have A times V plus W, then it should be equal to A times V plus A times W, and similarly A plus B times V must be equal to A times V plus B times V. So similarly, so these are very straightforward features and fairly intuitive as well, and I might even try to prove them in upcoming videos. We will see about that. But it's not really that difficult to understand this. It's fairly intuitive and straightforward. And similarly, it should have the associative property, which means that um, if I so if we have A into B times vector V, this is same as AB times vector V, and it is also associative with respect to addition, which means that V plus W plus Z is same as V plus W plus Z. Okay, so let's continue this. Similarly, it has the property of being commutative, which means that if we add W to V, it is same as adding V to W. Okay, this is also straightforward because you have done this in normal addition as well. But of course, the rule that we define for the rule of adding two vectors must satisfy these properties as well. And these two are again interesting. So there must exist something known as a null vector, which we denote it as with this symbol and the name 0, such that if we add this null vector to any vector v, the result of addition must be equal to the same vector v itself. Okay, and similarly we should have an inverse vector under addition, which we call minus v, such that if we add these two, we should get a vector which is a null vector. Okay, so if you have a set of objects where you can define addition and scalar multiplication and satisfy all of these properties which we have discussed so far, then such a set can be mathematically called as a linear vector space. Okay, if any of these properties fail, then such a set doesn't form a linear vector space, and we are going to see some examples in the upcoming videos. Okay, so before we end, one last topic, which is called field over which vector spaces are defined. So the set of numbers which we basically called as scalars, which we denoted with a, b, or some small letter, whatever notation you want to give, which are, so these are basically scalars which we use to multiply vectors and form a linear combination of these vectors and so on. So these numbers are called a field, okay, over which the vector space is defined. So what this means is that, for example, if we have such a linear combination, then if this combination is obviously going to result in a vector, because a scalar b multiplied by a vector w should belong to the should also be a vector. Similarly, a times v should also be a vector according to the properties that we have discussed, and a, so this vector plus this vector, since it is closed under addition, must also belong to v. So this is provided each of these belong to v. Okay, but if the condition is such that this is true only if a and b are real, then we say that the vector space v is defined over a real field. Okay, so for such a vector space we call it as a real vector space. And similarly, if such a combination results in a vector which belongs to v, if this condition is true for a and b, which are complex numbers, then we can call v as a complex vector space. And similarly, we can define many other fields as well, but we need not bother about them because mostly we will be working with the complex vector space. Okay, so with that, I would like to end this video. So thank you for watching and see you on day 2.